So hi everyone, I welcome you to the fourth lecture of class 11 that will be on mechanical properties of fluid. So today I'm going to start the next chapter that is the mechanical properties of fluid, and in this chapter. So hi everyone, I welcome you all to the fourth lecture of the series. So here I will be going to discuss the next chapter that will be on mechanical properties of fluids. So while discussing mechanical properties of fluid, it is important to know why should we need to study this? Why fluid is important? So, why fluid is important in general? In our surround, we need to look at our surrounding, and fluid is to study fluid and fluid mechanics or statics or dynamics. It is very important uh, because of its large number of applications in our surroundings. So I have shown some of the applications, and we need to convince ourselves that why we need to learn this concept of fluids and fluid properties and all the concepts related to the fluid flow and all. So first example I have taken is of cooler. So if you see that cooler, so when there is a fan, when you switch on the cooler, then the fan blows some cool air in the surroundings. So what happens to that? That when these cool air come into the surrounding, the hot air in the surrounding will mix with this cool air, and that will help in reducing the temperature of the atmosphere. But why I'm taking this example is because fluid is something that exerts a force on object. So here are the so with this fan, we are basically, it's a forced convection. So don't worry what is forced convection and all. It all will come with when you will go to BTech or anywhere else. But my primary aim is to tell you that why fluid is important. So here is the fluid is flowing. So fluid here is actually air that is flowing from this cooler to the surrounding, which gets mixed with the surrounding, and it makes the environment cool. Another example is that this is a dam where you see where you see a fluid, a liquid fluid in the form of liquid is flowing at a very high speed. So here at one side, so here at one side you see that the fluid is, so here if you see that the height of the fluid compared to another side is very high. So at this side fluid is stored at a very higher altitude, and because of that it has a high potential energy, and due to that potential energy fluid is flowing, and this fluid is converting uh, this fluid energy can be used as a power source, and that's where dam is used for the generation of electricity. So another example, don't worry too much about that how what is the mechanism behind it. I am just telling you that fluid is, we are surrounded by the fluid, and fluid is very important for us, and to know what are its properties from a fundamental micro level to the at a very high level. Here is there is another fascinating example that you know that fluid is something that causes an airplane to fly, and this is something. So I am came from the background of fluid mechanics, and this is something that fascinates me to study fluid mechanics. And so if you see this example of aeroplane, so basically fluid is flowing around these wings when and how it is happening, like these are the engines which is providing a thrust to the aeroplane. Due to this thrust, fluid is flowing through this wing. I will tell what is thrust and all why as we go along to this lecture. So as the fluid is flowing through this wings, due to this engine, it provides a lift to the aeroplane, and due to this lift, the aeroplane start flying to another altitude. Another example is a washing machine. So in washing machine, it is like a mixture where you add where you wanted to remove the dirt with the use of water, and what we do is we put our clothes in a tub in a tub of washing machine, and we make it move with a high velocity, and due to that what happen is water molecules goes inside the clothes. It is not just the water, it is the water with the surfactant, and there is another mechanism. So you see that in just this small example, we have a example of surface tension that removes the dirt from the clothes, and also the mixing part that causes that helps the fluid molecules to go inside the clothes. So that is a very nice example where fluid mechanics uh, is important. Another fascinating example is aerodynamics design. So if you see this picture, that is a Formula One racing car. So in this Formula One racing car, the design of this Formula One racing car is like that as it move along the drag, the design should be like to reduce the drag. So as it move along with a high speed, so the streamlines will go like this. So I will discuss what is a streamline and all with in the upcoming lectures. So streamlines will go like this. So the fluid is going like this as it go. If it is go in one direction, then fluid is flowing in another direction, and it is designed in a way that it feels minimal drag. So I should write few things about these examples. So here is the cooler. So air, which is also a fluid that is flowing from the cooler to the surroundings to reduce the temperature of the surrounding environment. In them, here the fluid is at so if you compare this, so it is at somewhat at height, and this fluid had some potential energy. So I will be going to discuss that what is that, but for now I'm writing. And this potential energy can be converted into the kinetic energy or the electric energy. So we with the use of kinetic energy, we move turbine, and then this will get converted into the electric energy. So in this case, the lift is given by this airfoils. So this wings gives it a lift, and this is very important. The angle of this wings is very important to control the speed of the aeroplanes in the air. The recent the recent crash that has happened in Nepal is because of the mistake of the pilot, where the angle of the wing is not. He wants to slow down the speed with the inclination of the wing, but he forgot to do that, and due to that, the speed would has not been reduced, and it gets crashed. In case of washing machine, so there is vorticity that is generating due to this mixing. So there is a sort of a steering around that. So it water is get water with the surfactant tries to go inside the clothes and remove the dirt particle from it and came out, and then it gets rain and dry. So this is the aerodynamics design. Okay, so these are the some of the applications where fluid mechanics is important. So now let's move on to the fundamentals of fluid. So basically, before going to know what are the different properties of fluid, we need to know what is fluid actually is. We have already learned about a solid. So solid is something, if I compare the fluid and solid in a way, that if you have a solid and you have a fluid, fluid consists of liquid as well as air, and uh, sometimes solid also behaves like a fluid. That are very special cases. I will not going to discuss those here. So let's say you have these parallel plates and this solid, you put a solid inside them. Now you apply a shear stress. So I have already discussed what is shear stress. So let's say you applied some force on this plate, and due to that it gets deformed. It gets deformed. But in this case, when you apply a force, it gets deformed, and it has, if it loses the elastic limit, then it is in a position that it will not going to resist that deformation and not able to come back to its original position, and it will remain deformed in that way. But in case of fluid, if you have a plate and let's say you have a fluid, I cannot confine a fluid in, so it is completely a fluid, and then you apply a force here, a shear stress here, then what will happen is, let's say at t is equals to t1, it is t is equals to 0, it's like this. As you apply a stress, if you consider this element, so at t is equals to t1 is this, t is equals to t naught, it is like this. At t is equals to t1, it becomes this. At t is equals to t3, at t is equals to t3, it becomes this. So what we see is that as you continuously, as you just apply a force, so the deformation is continuous. Deformation is continuous. So in case of fluids, the important distinction between the solid and fluid is that fluid does not resist the stress, and it has a continuous deformation till it reach a steady state. Okay. So that is the difference between the solid and a fluid. When we discuss about fluid or the properties of fluid, or why need to we study the properties of fluid? So we need to study the properties of fluid because we need to study what is fluid mechanics. Properties of fluids are important to learn the fluid mechanics. And fluid mechanics is basically divided into two parts, that is statics and dynamics. So fluid statics is nothing but the fluid is at rest. And the example of fluid statics is like you have let's say mug, and you have water in this. So this is the mug and you have a water in it. The essential condition we are considering that it will not going to get evaporated. That is the basic assumption, and that's why if there is no evaporation or nothing else, then the fluid, and you are not moving it, then it will remain at rest. And we need to study uh, what are the different forces that are applicable at different areas as you move along the height. What is the pressure acting in the horizontal direction or in the vertical direction? So all those things will come as a part of fluid statics. Fluid mechanics is fluid dynamics basically is a very broad range. Fluid dynamics is having a very broad range of classification, and it also consists of itself with kinematics. So in case of kinematics, we don't want to know about the forces that are causing the flow. So it is basically we decouple the sources or the forces from the dynamics part, and just want to know how fluid is flowing. We don't want to know what are the forces acting on it. We just wanted to know, let's say, if this is a pipe. So if let's say velocity here is V1 and here is V2, and we want to find out the change in kinetic energy, we are not looking what are the forces making this flow. We are just calculating the change in the kinetic energy of this uh, fluid particle at this point and at this point. So that is the kinematics. Dynamics is something that covers everything, all the aspects when fluid is not at rest. It will account all the forces that are important in describing the physics of fluid dynamics. It may have surface forces like shear forces, or it may have uh, body forces that includes forces on a fluid parcel due to gravity or any external field, like in case of electric field. If you have if you are having a charge carrying fluid, then it may have a finite amount of amount of body force, Coulombic body force. These are just example. These are just some greater details and some examples. But what we are interested in today's lecture is to know what is the fundamental definition of fluid, why we need to learn about these concepts, and some of the fundamental properties of fluids. So before going to start, uh, so first, as a property of fluid, we will be going to first study the pressure. So before going to study pressure, we will first describe describe different types of fluid. But in order to describe different type of fluid, I need to define different fundamental fluid properties. So why these fluid properties? Because these are the fluid properties that are these fluid properties will be going to describe the type of fluid. Okay. So if uh, if we say whether the fluid is, let's say, compressible or incompressible. Okay. So before going to those kind of details, I would like to discuss the fluid properties. So first is, so density is nothing but the mass per unit volume. So let's say if you have this cube, if you have this cube and the volume of this fluid is V and the mass of fluid stored in it is m, and density is defined as m by V, and SI unit is, that is kg per meter cube. Another property is that is very important, that is viscosity. So viscosity, in a very easy term, I would like to say that it is the resistance applicable to the applicable to the or more easy way, when you apply shear force over a fluid and the resistance provided by the fluids, layer of fluid is actually a viscosity. If fluid does not offer any resistance to the shear, any resistance to shear, then it is called to be a inviscid fluid, and inviscid fluid has having a viscosity 0. Viscosity is generally shown using the symbol mu. That is uh, called to be a dynamic viscosity. For kinematic viscosity, it's become mu by rho. And this mu by rho is shown like this. So mu is nothing but mu by rho. That is kinematic viscosity. So when the density of the fluid is changing, then we generally use the kinematic viscosity for the understanding of the fluid dynamics. So that is density, viscosity. So now let's discuss what is ideal fluid. So ideal fluid is fluid that is incompressible, that is rho is equals to 0, as having a fixed volume, then inviscid, that is mu is 0, then only fluid is considered to be a ideal fluid. If density is not 0, then fluid is compressible. Okay. So today we will be going to start fluid statics. So fluid statics, when we will going to start the fluid statics, then the first thing that came into our mind is to study pressure. So pressure is defined as so there are many wrong ways to define the pressure that has been generally used by many people. So what do you think the pressure is? So let's say this is the area. Is it this force per unit area? This is a tangential, this is normal on this surface. So is it tangential force per unit area? Is it normal force per unit area if we want to find the pressure at this surface of area having A? The pressure of acting on this surface, let's say this cubical box is placed inside a bulk liquid. So it is immersed in water. And now if you want to find the pressure on due to this fluid exerted on this surface, that comes out to be Pressure is also defined as the thrust per unit area. Thrust is nothing but the perpendicular area. So the pressure acting perpendicular to that area. But you cannot define pressure to be tangential force per unit area. And another thing is pressure is, so some of the fundamental thing about pressure is isotropic. So isotropic means it does not vary along the direction, or it does not vary along the space. It is same along all the directions. But that depends upon that force per unit area and which forces you are taking. That is the thing. So at molecular level or in general, pressure is isotropic. That is important thing. Another thing is pressure is scalar. So as you know that pressure does not depends on the direction in space. So it is scalar as it is directionally independent. So if you consider this box also, so the pressure acting due to this fluid at this side on this side is equals to the pressure acting at this side is equals to the pressure acting at this side is equals to the pressure acting at this sides, also this side and opposite sides. So that is what we meant is isotropic pressure. The SI unit of pressure is the SI unit of pressure is Pascal or Newton per meter square. And we will encounter some questions where the unit of pressure is will be in ATM, that is most commonly used, and it is nothing but 1.013 into 10 to the power 5 Pascal or Newton per meter square. 1 bar is also used, that is 10 to the power 5 Newton per meter square. 1 ATM is also there, that is 760 mm of Hg or 76 centimeter of Hg or 760 torque. And some of the conversions of volume sometimes you may not know. So that is 1 liter is 10 to the minus 3 meter cube and equals to 10 to the power 3 centimeter cube or equals to 1 decimeter cube. So now because now we are looking at the statics, so let's see the variation of pressure in horizontal in perpendicular direction or in the vertical direction. Variation of pressure in a vertical direction. So let's say we have a bucket that is filled with water. That is a bucket that is filled with water, and consider that pressure at this point is P1, pressure at this point is P2, or let's say where is it is exposed to the atmosphere. So it is exposed to the atmosphere. So here the pressure is nothing but P naught. Here the pressure is P1, here the pressure is P naught. And let's say the height in between the 2 points is, let's say, H. Now we need to find what is P1 in terms of P naught. So to calculate that, consider a cylindrical element of the same height H. and zoom out. And then we make a free body diagram of it. So here the pressure is P naught. Here at this point the pressure is P1. The weight of this fluid is acting in this side, that is W is equals to mg. Mass carried by this fluid element. So by applying force balance, let's say area of this is A and this also has having the same area, that is A. So P naught into A plus mg comes out to be P1. Okay. So M is nothing but rho density that I already defined into volume. So volume of this fluid, or you can define this volume as rho into area of this area, and this is H. Height of this fluid element is H. Okay. So that is how mass is defined. We put it here. It is also. So P naught A plus rho A H G is equals to P1 A, and P1 comes out to be P naught plus rho G H. So that extra term is due to the body force of the fluid parcel. So that is adding to that pressure in the fluid statics. And in general, in case of fluid statics, if you want to plot pressure with height, then you see that it is P naught, let's say, and it is linearly increasing with height. Slope, that is tan theta, tan theta is not here is nothing but rho g. Let's quickly discuss pressure in the horizontal direction. So variation of pressure in the horizontal direction in fluid statics. Keep this in mind that we are currently studying the fluid statics. So variation of pressure in horizontal. So we have this bucket of fluid. And now we are considering, because we want to see the horizontal variation of pressure in the fluid statics, they were considering the again cylindrical element in horizontal direction. If you zoom it out, then it will be like this. And if you do the free body diagram of this figure, then that is P1, let's say this is P2. And if you do free body diagram, then P1A area SA is equals to P2A. So P1 is equals to P2. So in fluid statics or non-accelerated fluid, the pressure is same along horizontal line. So if you go along, let's see, if you take this line, so pressure at all the points along this line is same. So in this case also, however we take a small elements, we didn't take this part, but whatever the pressure you calculate at this point or this point or this point, it will be the same at this point, this point, this point. So P1 is same at all the points. So that what we have described here. So that is the important thing. In case of fluid statics or the non-accelerated fluid, the fluid does not vary along the horizontal direction. In the vertical direction, it is only varying because there is a gravity. If there is no gravity, then there shouldn't be any variation along this, and this variation is essentially because of the mass that is coming from the external field, that is gravity. So that is variation in pressure in along horizontal direction, and that is variation in pressure in vertical direction. Now, before I end this, I will be giving you one question and try to find out the solution to that. That's the simple question. So let's say you have a different kind of vessels as shown in figure below. The height of the fluid stored in each vessel is same. Relate the pressure at the base of each vessel. So let's say you have this tumbler like this, you have something like this, you have something like this. So now we have three kind of vessels, and let's say this is A, this is B, this is C, and fluid is filled here till the height H. So all are at same height. The options are PA, PB, PC. PA is equals to PB is equals to PC. PA, PB, PC, none of the above. So tomorrow I will start with this question and will try to prove the solution of this question using two different shapes. So that's all for today. So this is the fundamentals that we have discussed as a part of fluid statistics. Tomorrow we will be going to start with this question and we'll move along with some of the previous year questions also. Okay, thank you.